Same thing with changing variables in multiple intervals. So actually, if you think about the idea of changing variables, we have seen that. So if you were a rectangular system of coordinates, a rectangle is a rectangle. But now we have also introduced, other coordinate systems. So let's firstly sketch a rectangle in the XYZ space. So if you talk about the rectangular box, what you're doing is actually fixing x within a specific interval, and then y variable in another specific interval, and z in another specific interval. That's exactly something like the interval AB cross the interval CB cross the interval x. Right. So basically, everything here has to do with the intervals of each variable that you're putting together, right? And that's definitely a shape of a rectangle. But now, another rectangle in cylindrical in the cylindrical coordinates is definitely different. So, and sketches. What happens if we're at a cylindrical? Let me do it like this. So if you're thinking about cylindrical coordinates, then in the z coordinate is where the cylindrical shape comes from. But in terms of the xy plane in the horizontal direction, so in the horizontal direction, if you're looking at the bottom right here, this is exactly like a circular sector, right? But then this definitely gives you another shape. So although this thing looks like this is called a cylindrical box. But here, it's not really a box in terms of the XYZ space, if you think about it. It's actually the R theta D space. Okay. Because in terms of the cylindrical coordinate, we have R, which is the radius from A to B. That's it. So the inner radius right here has a radius of A, and the outer has a radius of B, right? So that's why we have this sector. And then for the angle theta, that's from, let's say, from alpha to beta. And that's actually deciding this two sides. Okay? And that's the kind of the limiting value for the angle within the XY plane, right here. So this ray represents the angle alpha. This ray represents the angle beta. Right? And finally, z is let's say between s and t. S. And the z value gives you the top and bottom. Okay, gives you the height. But now, so if you're looking at this here, if you're looking at this cylindrical box right here, we're defining everything in terms of r, theta, and z. But now the formulation looks to be exactly a rectangle, but it's in a different coordinate system. Right? So this is also a b cross alpha beta cross s and t. But it's in different coordinate system, right? In theta z, right? And now, if we draw that system out, it will be something really similar to the left-hand side rectangular box. So the point here is that this three intervals, it will cross and get you a rectangle right like this. Okay? But if you translate it in terms of x, y, z, according to a system of equations, we will get this one. And this is exactly the change of variables. And we have seen this, we have seen the way that we translate, because x is exactly r cosine theta, right? Y is exactly r sine theta. And finally, z is z. From this translation, you see, we transformed the red rectangle into this black cylindrical box, right? So the original shape is really nice, and you can calculate the volume easily. But you see the translated solid has a harder volume that you have to relate to this system of translations that you should do. And there's indeed this volume issue that we'll be discussing. And if you recall, we have already discussed this kind of a volume factor. There's an r dr theta, right? When we were talking about the accumulation of volumes. All right. We also have seen another one as a spherical wedge. So what happens is in a spherical system, you have x, y, and z right here. If you look at a spherical box, it will wedge. So we have the nicer figures in the previous section, so I'm not gonna repeat that again. But if you think about this, this is a sector that's perpendicular to the xy plane, and this is in the same plane as the z-axis, right? But then there's a sector, and you revolve it along the z-axis in a way, so eventually you will get something like this. Right. That's the batch we have seen from the section 16.5. And similar to the previous figure, is also translated from another system of rho, theta, and phi. Right? We have one distance and two radians. But it will still be a rectangle that we would translate into a wedge. And if you think about the way that we translate, this is exactly x equal to rho sine phi cosine theta, y is rho sine phi sine theta, right? Finally, z is rho cosine. Right? So if you recall, p is the angle from the z-axis rotating to your point, right? And then theta is exactly the projection that you do into the xy plane and then get that angle from the polar coordinates xy. Okay. So the spherical box, if you think about it, is exact same kind of formula. Intervals is interval crossing, but it's in a different coordinate system. It's in rho, theta. Okay. So it's rho, theta, and b, such that rho is between a and b, theta is between alpha and theta, and b is between c and e, different angles. But once again, you will be translating a rectangle in this rho theta phi space into this wedge. Okay. But still, okay, the volume of the box in the original system is definitely easier to compute. But then, how do we compute the volume of this new wedge that we translated from through this method? So this is the second question we have in mind in this section. Okay. So the fundamental thing is that we always have some kind of variable system, and we always have a rectangle, but then how are we going to compute the volume that we result from the translation, the change of variables, the translation of variables? Okay, so now, if we look at these two examples, what do we see in common? So of course, we always start with a rectangle in some space. Let's say right here or right here, we have a rectangle. It will be a rectangular box. Okay? But then we have also the translation in red. This is translating from r, theta, and z in a certain way into x, y, z. Okay? We have another way of the translation from rho, theta, and phi into x, y, z. And eventually we got some solid, either in black right here or right here. So we definitely want to get the connection, but we can make it even more general. And let's introduce what's called the Jacobian determinant. Right. So let's think about these two systems, one in red, one in black. So the original is gonna be called UV and W. So if we have X in terms of G of UVW, where G is some multivariable function, Y is the result of some function H translating from UVW, and Z is, let's say, some function in terms of UVW. Okay. So basically here, this is exactly translating from the system, from the coordinate system UVW into the new system XYZ, right? Every coordinate is some multivariable function. Then the Jacobian determinant is the following. We will put in the relation J of UVW. You see everything in terms of UV and W, right? So it's going to be a function which is calculating. Notice we have three multivariable functions. So let's put the first order partials of the first variable x, okay? First function x in the first row. So it's del x del u, del x del v, del x del w. And then we put the second variable, all the partials in the second row. So it's del y, del u, del y, del v, del y, del w. Finally, the third variable, we put the things also in the third variable, in the third row. Del z, del w. And if we compute this 3×3 determinant, that's the Jacobian determinant that we want. All right. So we have the formula, but what does it mean? The Jacobian determinant J of UVW describes the change of volume from coordinate system UVW to the coordinate system XYZ. Okay. All right. So basically here, when you want to know the connection between from the old volume to the new volume, it's just going to be the calculation of this. Example. If we think about the first question that we had in mind, is cylindrical. Coordinate. We have what? We have x equals r cosine theta, y equals to r sine theta, and z equals to z. So here, this change, the system, this coordinate changes from r theta z coordinates system to XYZ coordinate system. Moreover, we definitely can do the partials and put everything together, right? And write down the Jacobian determinant. So here, okay, the first way of thinking about Jacobian is that, okay, I put every first order partials in the first row, okay, from the first variable. For the second variable, I have everything in the second row. The third variable gives everything in the third row. But now, if you are doing the partials, you can also think about it in this way. So the first column is all the partials in terms of u, in terms of the first old variable, and second column is everything about v. The third column is everything about w. Right? And then this is going to be a little bit easier if you are just doing the partial derivatives. So now let's look at x, y, z, and now let's do the first variable is r, right? So we do the first of all the partials with value r. So it's going to be a cosine theta here, sine theta in the second row, and 0 in the third row. Excuse me, column. Yeah, I think I said it right. So we put everything here in the first column. The first row is going to be cosine theta. The second row is going to be sine theta. Third row is going to be 0 because it's differentiated with value r. I'm doing the partial value r. Now, with respect to theta, so from x we will get negative r sine theta, and then r cosine theta, and then 0 because we're now differentiating with respect to theta in the second column. And now for the third column, so we now differentiate with respect to z, right? So it will give you 0, 0, 1 because x and y they have no z's. Right, so this is exactly how we set up the determinants, but then it's not over yet because this thing always can be simplified if we break it up, right? So this is all the three determinants. So if we calculate, this is going to be, so think about the definition. So it's going to be the first row, first column multiplying by, you made the first row and first column and have the remainder r cosine theta 0, 0, 1 that you must compute minus the first row, second column multiplying by the remainder of if you eliminate first row and second column, it's going to be sine theta 0, 0, 1. Finally, we need to plus the first row, the third column gives you a 0. And so you don't really need the elimination anymore. So, and simplify. So it's going to be, you see the first determinant, 2 by 2 is going to give you r cosine, right? So it's going to be r cosine squared. You have 2 minuses that gives you a plus. And then sine theta times 1, right? That's giving you r sine squared theta. And now, okay, when it simplifies, you see r sine squared, r cosine squared adds up to be r, because we have the identity, which is the Pythagorean theorem. So you see here, the translation tells you it's going to be it's going to introduce you an additional r if you want to switch the volume from one to another. So note that the v that we were having for the cylindrical coordinates is r dr d theta dv dv. Okay. So this r is exactly this r under cylindrical coordinates. So this is a even more systematic way of computing this additional factor r that you have to keep in mind, right? So that's good. All right, we still have a few minutes, so let's at least start the other question that we started with in this section. So example, now we want to consider the spherical. So if you really consider this procedure, it's going to be really standard. So for spherical coordinates, we have x equal to rho sine phi cosine theta. Y is rho sine phi sine theta, and z is rho cosine phi. Okay. So if you're looking at the system, it definitely is a little bit more complicated, but still we have a univariate function, another one, and another one. Okay. So it's going to be the same process. We have the Jacobian determinant defined in terms of rho theta v. So the only thing that's a little bit tricky here is that you definitely need to put down the order of the three variables really clearly, and then you're just gonna do the computation with respect to the same order. So if we're doing the first variable to be rho, and then we just do the partials for x, y, z in terms of rho, and we'll put them in the first column. So it's going to be sine phi, cosine theta, sine phi, sine theta, and then finally cosine. And then if we're differentiating now, the second variable is theta, right? So it's going to be rho sine phi is negative sine theta. And here it gives you a cosine theta. And finally, z has no theta, then it's going to be a 0. And finally, for calculation of phi, is going to be rho cosine phi, cosine theta, rho cosine phi, sine theta, iteration with certain p. And then we have negative rho sine. Okay. Okay. So after a few steps that I will write down a little bit details later on in class, but eventually you will get negative rho squared sine. Okay. So still, this is just all the three determinants that you should be able to compute. But then if you throw away the sign, you will see, okay, this is rho squared sine phi. Okay, that's something very similar. That should be very familiar with you. Okay, so it's going to be that expression that you need to keep when you are doing the spherical coordinates. Okay. Right? These are exactly the same thing. Okay. The only difference is actually the sign right here. But in terms of the absolute value, if you want to compute the volume, it will go away. So, and of course, you can definitely think about more general systems of translations yourself, and then so this Jacobian determinant will tell you how much volume translation you will need to consider in this kind of translations.